Alright guys, we're going to go ahead and finish out our metabolism notes, and the second half is all about enzymes. And so the first half was about metabolism, and the reason we're talking about enzymes with metabolism is because enzymes essentially regulate all of the metabolic activities that are going on in our bodies. And so enzymes are something we need to be very familiar with, and one of the things that we definitely need to understand is that enzymes are proteins, okay? And so something that we talked about when we did our macromolecules is that proteins take on a very specific shape. And in this lesson, you may see the word conformation, and conformation, anytime you see that, is referring to the shape, okay? And every protein has a specific shape, which gives it a very specific function. All right, so that word specificity or specific, every time we talk about proteins, that word is going to be used because of their very unique and special twists and turns and globs. That's going to mean that protein can do a certain job. They aren't multi-purpose typically. And so by definition, an enzyme is a protein catalyst, okay? Now, what follows is the definition of a catalyst. A catalyst is anything that speeds up a chemical reaction by lowering activation energy. Okay, so catalysts are molecules that speed up chemical reactions. Now, protein catalysts are the main ones. Normally, if you're talking about a catalyst, you're talking about enzymes. But there are some other molecules, there's some RNA molecules that can act as catalyst. And so catalyst is a more general term, and then enzyme is a specific type of catalyst. It's a catalyst that's a protein. And so what enzymes do is they speed up reactions, and how they do it is they lower the activation energy. And so we do need to understand what activation energy is. So all reactions, whether they're endergonic or exergonic, it doesn't matter whether energy is going in as a whole or energy is coming out as a whole, all reactions require an initial investment, okay? And we call that the activation energy. I like to just simply refer to that as a push. All reactions need a push to get started. Some require a bigger push than others. Typically, if they're spontaneous, they're going to have a lower activation energy. If they're non-spontaneous, they're going to have a higher activation energy. But all reactions are going to require an initial push. So there's some energy needed to break some of the bonds of the reactants to get the reaction started. And most of the time, this is going to come from the heat of the surroundings. Now, the problem is that waiting for this activation energy can take a long time. And so the reason we need enzymes is they help speed up those reactions and make them happen a whole lot faster. Now, enzymes are not a reactant and they're not a product. Okay, they do not change the overall result. We're essentially going to start in the same place. We're going to end in the same place. The same amount of energy that was going to be released, that's not going to change. The same amount of energy that was going into the reaction, that's not going to change. The only thing we're changing is the activation energy. Okay, the overall energy change is staying the same. So they don't change the reaction except for making it faster. Okay, now they are selective. This goes back to that word specific. So it's not like there's one enzyme that goes around and catalyzes all of the reactions in your body. They're going to be picky, and it goes back to their shape, okay? And so if the enzymes are present, that's going to pretty much decide what chemical processes are taking place. So one thing to kind of help you understand this is if you think about your organs, a lot of your organs do different things, and the reason they do different things is because they contain different enzymes. So the enzymes essentially determine the reactions that are happening at those locations. All right, so you actually have a picture like this in your study guide, and I would encourage you to look at it. Okay, your study guides are not pointless. In fact, you have a couple of pictures in your study guides that deal with enzymes, and this is one of them. And so you are very likely to see a graph or multiple graphs on the test that you take for biochemistry. So this is something you want to pay attention to. So notice that this graph is showing the progress of reaction over time, and what we're looking at is the free energy. That was your energy available to do work. And so here you have the energy of the reactants. Now notice that the red and black lines are starting with the same amount of energy. Okay, here's my products. Notice that the red and black lines are ending with the same amount of energy. All right. Now, just to kind of test you on what we covered yesterday, notice the overall reaction. By looking at this, we should be able to tell whether it's endergonic or exergonic. All right. So in this case, the products have more energy, which means energy must have gone in, and therefore this is an endergonic reaction. Now, that's really not what we're looking for in this particular graph, but I just kind of wanted to remind you of that. You should be able to tell from a graph what kind of reaction it is. Now, what we're worried about here is the hump, okay? Notice that in both lines, the graph goes up initially, okay? Every reaction is always going to go up initially in energy because of activation energy. Now, what's different between these two graphs is the hump, okay? So the reason this hump is lower is because there was an enzyme or there was a catalyst present, all right? Notice that the activation energy is lower. So the start is the same, the end is the same. The only thing different between the two is the hump, and that's because enzymes or catalysts lower activation energy. Now, what that does is it's going to allow us to get from here to here faster, but it doesn't change where we start, and it doesn't change where we end. It just allows us to get there at a faster pace, okay? So when we say activation energy, that's the hump, and enzymes lower that hump. All right, so how do they do it? How do they actually work? Okay, we have some important vocabulary here. So first we have the substrate, and the substrate is the reactant or the reactants. So in a chemical reaction, you always have reactants on the left and the products on the right. So in the case of enzyme activity, the substrate is whatever's over here. It could be one thing, it could be more than one thing, okay? But the substrate is just a reactant. It's going to be some type of chemical or element or compound, whatever it is, that's going to be our substrate. Now, the active site is a location on the enzyme. Now, a lot of times when we draw enzymes, they are kind of cartoony looking. They're just kind of shapes, you know, like pies or Pac-Man or something like that. But I want you to remember that in reality, this is a highly complexly folded protein, okay? And so what you've got are you've got these little nooks and crannies, and anytime you have these places on a protein, things can bind there, okay? So in reality, it's that tertiary or quaternary structure protein that's highly folded and globular. But the active site is the particular location on the enzyme where the substrate is going to bind. Okay, so active site is on the enzyme, and it's where the reactant or the reactants are going to bind. Once again, very specific. Okay. Now, what's going to happen is the reactants are going to bind to the active site. So the substrate binds to the active site of the enzyme. Now, one thing you have to understand is that it just happens, okay? These molecules, these chemicals just happen to be in the same place at the same time. Okay, keep in mind these are chemicals. It is a chemical thing. It's not like the substrate is actively looking for the enzyme or the enzyme is actively looking for the substrate. We're talking proteins and chemical compounds or elements. So all you need to understand is that they just happen to be in the same place at the same time. And because their shapes are complementary, they are able to come together. Okay, so when the substrate binds to the enzyme at the active site, they now form the enzyme substrate complex. Now, this is going to be like this for a very, very short period of time. Okay, think about how quickly a chemical reaction can take place. You mix the two chemicals together and boom, you start to see signs of the reaction a lot of times. And so this is going to be for a very short period of time. Now, it is specific, okay, in kind of freshman biology, a lot of times we describe this as like a lock and key, and that the right lock has to fit the right key in order to open it. It kind of goes the same way, but it's a little more specific than that. So I like to think of induced fit of like a broken in pair of shoes. Think about your favorite pair of shoes, maybe a pair of Birkenstocks or Crocs or even a pair of tennis shoes. You know, when you first buy them, you buy your size. So like I'm an 8.5, so when I go to the shoe store, I'm going to buy a shoe that's 8.5, and that's going to fit anybody that has an 8.5 size foot. But as I wear that shoe, it starts to make little tiny changes based on the pressure points and how I walk. And over time, that shoe begins to kind of mold and fit my foot perfectly, making it a really solid fit and a comfy fit, okay? The same thing is going to happen with this substrate and enzyme. The substrate is going to bind to the enzyme because the shapes are complementary. They're like the same size shoes, okay, to my foot. But once it binds, there's going to be these little tiny changes in the shape of the enzyme that's going to allow it to fit perfectly, okay? So as it enters the active site, the induced fit is when that enzyme makes little tiny subtle changes to better fit the substrate, okay? So the substrate binds to the enzyme at the active site, and little changes are made to make it fit perfectly. It's a little more specific than just your basic lock and key. All right. So once the substrate binds to the active site, it forms the enzyme substrate complex. There's going to be some weak hydrogen and weak ionic bonds that are going to hold it there very temporarily. And then at this point, the reaction is going to progress. So remember, you have your reactants on the left and you have your products on the right. So what's going to happen is those reactants or the substrate, when that activation energy is lowered, they are going to be converted into products. Okay, so the substrate will become the products, and then the enzyme is going to be unchanged. So the enzyme is just a helper. In fact, a lot of times, remember, it's not a reactant, it's not a product, so you'll see it written above the arrow or around the arrow. And so what happens is the substrate gets converted into products, the enzyme stays the same, and it can be used again and again and again with that same substrate, okay? Remember, the protein is not part of the chemical reaction. It's just a helper. So you really kind of need to know this. I don't know if this video link works, but there was a video attached. I don't think they work anymore because they were Flash Player. But what I'm about to repeat, normally in class I would repeat it about 5 times, but you need to know this process, okay? So the substrate, which is the reactant or the reactants, in this case there's just one, okay? The substrate or the reactant is going to bind to the enzyme at the active site. All right. So remember, the substrate and the active site are complementary. When they bind, you have the enzyme substrate complex. The substrate will become products, and the enzyme can be used again. Okay. Now you have a picture about enzyme activity in your study guide as well. It's not identical to this one, but it's similar. And you could very likely see a picture similar to this on your test. So be sure you know that the substrate binds to the enzyme at the active site, forming the enzyme substrate complex. The substrate gets converted into products, and the enzyme stays the same and can be used again. So in a picture, a lot of times people say, well, the enzyme is bigger or whatever. And technically it normally is, because it's a big old protein. But the way you can tell what is what is that the enzyme stays the same through the whole process. The substrate is what gets converted into products. And so you could very easily have 2 substrates forming one product. So it's not about the number either. It's about what you start with and what you end with. All right, so there's several factors that can affect enzyme activity, and this is what your lab is going to be over. Each group is going to have a different variable, and some of these are going to be the variables that you will be testing. And so one factor that can affect enzyme activity is temperature. Now, I mentioned earlier that the substrate and the enzyme just have to come into contact with each other. I'm really guilty of imagining it in my brain like they're living things that are looking for each other, but that is not the case. They both just happen to be in the same place at the same time. And because of that complementary shape, that substrate is able to fit into that active site. And so if you think about temperature, whenever it's cold, things are moving very slowly. And as we heat things up, they begin to move faster. Just everything, molecules, atoms. Colder equals slower and warmer equals faster. So if these molecules are moving around more quickly, they're more likely to kind of bump into each other and come into contact with each other. So typically, warmer is better. Okay, warmer is better. Warmer equals more enzyme activity. Colder equals slower. It doesn't mean they won't work, they're just not going to work as quickly. Okay, now there is a catch though. When it comes to temperature, too hot is very bad. Okay, too hot equals denature, and denaturing is when a protein loses its shape. So remember that these proteins have this very, very specific, highly complexly folded structure, all right? Now, what happens when it gets too hot is literally it unravels, okay? So this protein, if it loses its shape, is no longer going to work, okay? Denaturing means the protein cannot bind to the substrate. And so this is why a high fever is dangerous. And I'm not talking like 99, 100. I'm talking like 104, 105. I mean, we're talking very, very serious, because if your body temperature gets too hot, your proteins will start losing their shape. And so denaturing is not good. Every enzyme has its own optimal temperature. Like in the human body, it's going to be about 37 degrees Celsius. That's our body temp in Celsius. Now, if you were a bacteria living in a hydrothermal vent, their optimal temperature is going to be a little bit different. But in terms of us and our enzymes, it's around body temp, which is 37 degrees Celsius. So your temperature gets too low, enzyme activity slows. Your temperature gets too high, activity will increase up to the point that it's dangerous, and then denaturing will occur. So too hot is definitely going to be bad. All right, another factor that can affect enzyme activity is pH. Once again, every enzyme has an optimum of where that works best. In our body, in most places it's around neutral, like in your blood and in your body tissues, it's going to be around neutral. But like for instance in your stomach, where you have an acidic environment, the enzymes that are in your stomach are going to have a more acidic optimal pH. But like temperature, extremes equal denature. So just like the temperature can make denaturing or unfolding occur, so can extreme pH. So if the optimum is 6 to 8, if you start getting, down into 4s and 2s or 10s and 12s, that denaturing could occur. Okay, this is going to be another factor that's going to be tested in your lab. And so the main thing is they're going to work best in their optimum range, and then if you go outside of that optimum range, that enzyme activity will decrease and sometimes just stop altogether if denaturing occurs. All right, another factor is concentration. Now, if we're waiting for these molecules to come into contact, the more of them there are, the more likely they're going to come into contact. So typically, increasing concentration is going to increase enzyme activity, and whether that be the concentration of the enzyme or the concentration of the substrate. Now, we'll talk about non-competitive inhibition here in a moment, and that may make sense once we cover that. All right, cofactors can affect enzyme activity, and so think of these like helpers. Now, what they do is they bind to the protein and they help the protein take the proper shape, okay? If it's an organic molecule that has carbon, we call it a coenzyme. But essentially they're things like vitamins or other little compounds that they bind to the protein somewhere else and they help make it active. So cofactors could increase enzyme activity if they're helping those proteins take the proper shape. And then we have inhibitors. Now, by definition, inhibit means to stop or slow down. So inhibitors are going to slow down enzyme activity or stop enzyme activity. That's not always a bad thing. Sometimes we need to turn a pathway off. And there's two types of inhibitors. There's competitive and non-competitive. Now, think about if you are competing. Normally you are trying to win. You are competing directly with something else. And in the case of a competitive inhibitor, it's competing with the substrate because it has a similar shape, okay? So the reason it can inhibit or stop enzyme activity is its shape is close enough that it can get into the active site, okay? So the key is that a competitive is going to block the active site. So think about that lock and key thing. Sometimes you have a key that will fit into the lock, but it won't actually turn. Now, if that key is in the lock, can the real key get in? The answer to that is no. And so what a competitive inhibitor does is by having a similar shape, remember these are just molecules that just happen to come in contact. By having a similar shape, it can get in there and block the active site. If the competitive inhibitor is there, the substrate can't get in. So this is going to decrease enzyme activity. Now, the more of the substrate you have, the better off it's going to end up in the active site rather than the inhibitor. Now, in a non-competitive inhibitor, it's not competing directly with the substrate. And the reason why is because it's binding somewhere else, okay? It is not blocking, it is changing the active site, okay? A non-competitive changes. Now remember that shape is everything. Now when molecules bind to proteins, it causes the protein to change shape. And so these inhibitors literally change the shape of the active site. And that substrate is never going to be able to get in. So it doesn't matter how much substrate you have. If you have a non-competitive inhibitor, then you're not going to have that binding taking place. So non-competitive change the active site, while competitive block the active site. Now this takes us to allosteric enzymes. Now allosteric enzymes are enzymes that are regulated by regulatory molecules, okay? So like that non-competitive inhibitor that we just talked about, that's an example of an allosteric regulator. So an allosteric site is just somewhere else on the protein where substances combined. So let's go back to that fancy protein shape, okay? All right, now let's say that the active site is here. There's still other nooks and crannies where other molecules could bind, okay? So the allosteric site is another site on the enzyme. And normally either something called an activator will bind or something called an inhibitor will bind. And so essentially the enzymes are going to have these regulatory molecules that determine whether they are active or inactive, okay? Essentially the active site is going to be available or unavailable. And so the key to allosteric regulation is the enzyme is changing between two conformational states. What that means is two shapes, okay? In an allosteric enzyme, they're either going to be in an active state where the substrate can bind, or they're going to be in an inactive state where the substrate cannot bind. So essentially the enzymes are kind of turned on and turned off by these molecules. Now, not all enzymes are allosteric. Typically those that are have two or more polypeptide subunits. And so this goes back to that quaternary structure. If it's just one polypeptide that's twisted and folded, it's probably not going to be allosteric. Normally these are proteins that have multiple subunits, like hemoglobin has 4, okay? So these are going to be the ones that are in that quaternary structure, okay? And so what will happen is if an activator binds, the substrate will be able to bind to the active site. If an inhibitor binds, it changes the shape, and the substrate cannot bind. And so what's going to happen is these enzymes are essentially switching between an active and an inactive state, depending on the regulatory molecules. Now, the good thing is that it doesn't take, let's say there's 4 individual allosteric sites, okay? It doesn't take 4 regulators to make it in that form. Usually it's just one inhibitor and the whole protein gets shut down, or one activator and the whole protein gets activated. So that's what we call cooperativity. A change in one subunit will lead to that same change in all subunits, okay? So once again, conformational change just means shape. So if an inhibitor binds, all of those subunits will be inactive. If an activator binds, all of them will be available. You don't have to have 4 separate molecules binding. And then the last thing we're going to talk about is feedback inhibition. Now this is also called negative feedback. Now this is something we cover in freshman biology. It's something we're going to cover again. Negative feedback is a process where you maintain homeostasis by turning on and then turning back off. Okay, it's kind of like a thermostat. If you have it like a set point, if you go away from that set point, then it triggers a response. But once you get back to that set point, you turn that pathway off. Okay, so it turns on and it turns off. That's where you get the word negative. It's actually a really positive thing. It's not bad at all. It's a wonderful thing. And so feedback inhibition is about not being wasteful, essentially. It's kind of like snow cone stands. You know, once we start getting cold weather, people don't really want to buy snow cones as much, so the snow cone stands shut down. And then they'll open back up in the spring when the weather gets warm, because there's just not enough people buying snow cones to merit making them all winter, okay? Same thing happens in our bodies. We don't want to waste materials. We don't want to waste, any kind of molecules or compounds or anything like that. And so feedback inhibition is where a pathway is turned off by its product, okay? And so what we are going to see is kind of like a chain reaction of chemical reactions. So what will happen is the final product of that pathway will actually act as an inhibitor. So once there's plenty of product, it'll kind of shut the pathway back down. And that way we're not making something that we don't need. We're not making snow cones when no one's buying snow cones. And so the picture kind of, to me, helps explain it better than the words. So here we have a metabolic pathway. Okay, we have several reactions that involve enzymes. Notice they're all different. Okay, and so what happens is, here's my substrate, there's my product. That becomes the substrate in the second reaction. There's my product. That's the substrate in the third reaction. There's my product. Now, at the end of the pathway, we don't want to keep making this here if we don't need it. Okay, we don't want excessive product. And so when that product builds up, this product actually serves as an inhibitor to the enzyme at the beginning. And so when this product builds up, it will bind there. Well, when a inhibitor binds, remember that changes the active site. And so what will happen is, once this product builds up, it binds to the original enzyme, it changes that active site, this substrate can no longer get in. So it essentially shuts that pathway down. Now, when those products are not as numerous and not as available, then more than likely that substrate can get in there. So feedback inhibition is about turning off. Okay, the end product acts as an inhibitor to turn the pathway off. And that's what feedback inhibition is. All right, that wraps up the end of our metabolism notes. Now, you had a little practice quiz for part 1. For part 2, we're going to be doing a lab. And so you may get your pre-lab today, you may not. Either way, you're going to have a whole day to work on your pre-lab, and you're going to have a lab poster, and I should be there to explain that to you on Friday. So I hope you guys have everything you need about enzymes. If you have any questions, just let me know. And this is also the end of our note material for our first unit test. Your unit test is going to include the review of chemistry and water properties, the macromolecules, and now this set of notes, which is metabolism and enzymes. So those are the 3 sets of notes that you will find on the first unit test. All right, I will talk to you guys soon, and I hope you all have a great day.